In our last project update, we featured the building of C3.2b, a research model with which we'll test the concept of supercavitating hydrofoils at speeds of over 200 miles per hour. The model will also be used to try out the advanced control systems needed to maintain stability at extreme speeds over water. At 3 meters long, C3.2b is a quarter-size replica of the planned full-sized TWSH Water Speed Challenger. It's powered by a jet engine intended for use on military drones, and it's packed with electronic systems, sensors, and electromechanical actuators. Before running at the speeds needed to test our revolutionary hydrofoil concept, the test program called for low-speed trials to check the control systems and safety features. As the team gathered at a private lake in Oxfordshire, they expected this to be a relatively simple step. But as you'll see, it was anything but plain sailing.
Well, this is the big exam. That's really what it's about. So the name of the game is that we're here at Berrinsfield and we're going to be doing our testing. And we've got to get the engine running. And then, of course, we've got to put the boat in the water. We've got to practice launching, recovering the boat, gradually moving up its speed range up to about 40 odd miles an hour. And just making sure that, that the boat responds. We can make the boat respond. In other words, that it's safe. So it's a big, big test because basically as an organization, we're a wonderful collection of people, but we're a sort of IT collection of people. In other words, basically, this is the first time people have come actually face to face. And it's great. It's working really, really well. There's a very, very good team ethic here, which is excellent. It's a great team of people, very, very experienced, and it's going to work well.
What we have to do is design a boat that behaves in the same sort of way that the full-size boat will. In fact, this boat will, movements in terms of angular changes will happen at twice the speed of the full-size boat. So actually the control system needs to act quicker than the full-size boat will need to work. So this requires a fast-acting control system that continually changes the angle of the hydrofoils that it's running on. We will need to also have instrumentation, because what we need to do is understand the loads that I've mentioned, but also the actual aerodynamics, the hydrodynamics, all those, we've got to actually identify what they are. Whereas on the full-size boat, you live with what you've got, but you've done enough work beforehand to know that it's safe. And this is part of the process of knowing that the full-size boat will be safe.
Well, this is the thing that we call the barge, a pretty unimaginative name, but functional. And it's designed to enable us to launch the test boat onto the water from suspended out in the lake, and also to bring it back to the pontoon, drop it onto the water, and then manhandle it onto the trolley, which is the land-based transport vehicle. So this is basically a water transport vehicle for the test boat. It is purpose-built by the very fine Williams jet tenders. They built this thing from scratch using the tubes off a rib, but not sticking it to a hull. So it is a hull-less boat. And they're also lending us one of their complete ribs to drive it about with. That's a 520 petrol, which is an extremely fine boat. We're very lucky to have it.
I'm Andy Blight. I'm from the University of Leeds, and our role here today and on this project is to write software to control the high-speed boat. The control systems that we're using, there's a custom printed circuit board with 2 processors on it, an ESP32 processor which we're using to do most of the logging and the communications with the base station. And then there's the Team Z, which is responsible for the high-speed control of the hydrofoils and the rudders.
We're going for another start. Over.
Roger that. Over.
Well, we always knew this project was going to be difficult, didn't we? And you know, we haven't really got the boat moving at all. I mean, but we have triumphed on a couple of areas. First is that we've managed to get the communications working. On the first runs, we had a lot of trouble with the communications. The Leeds team set about this last night and worked to God knows how many hours last night to actually get this right. And they came up with a solution, which is good. So this means we can actually run the model.
Over the following days, the team managed to run C3.2b several more times, but control issues persisted, and the first trials ended inconclusively. Plans for high-speed testing were postponed, and the model was returned to its base in Littlehampton for extensive modifications to the control systems. Finally, in mid-July, the team was back at the lake in Berensfield.
My name is Hitesh Bhardwaj, and I'm from University of Leeds. My role on the team is basically to design the controller for the boat. We have done major changes compared to the last test. First and foremost, we have selected better telemetry radio units. Previously, we were having issues because the signal keeps on dropping in and out, and after a certain distance, the radio basically just shuts down. So those sort of issues are no longer on this boat because of the better units that we have used now. Then we have also changed the GPS because we were facing issues that the boat was not able to connect to the GPS, was not able to receive the GPS signal because when it's sitting in water, there are issues because of the multipathing and all. The signal gets reflected from the water, or because of the frame, which is carbon fiber. So all those things have been eliminated. We have used a better GPS receiver as well as antenna, and that has helped quite a lot. We have also implemented kill switch now, which can be given to different observers around the lake, and just by pressing the button, if they see that the boat needs to be stopped in case of any emergency, they can press the button and that will stop the boat.
We learnt that the comms issues that we had last time we came to Berensfield, no issues with those, so that's a good start. We were able to start the boat remotely. We're getting data transmitted back from it, so we got a good lot of data from that. The boat set off in a straight line without steering input. Then we put manual steering one way, then the other. We learned how reactive the boat is to angles of steer at low speed, and that it went the right way, etc. So we got some good data from that. We then switched into an auto steer mode where it's due to head to a particular point in the distance. It veered off to one side, not heading towards that. Now, at the moment, we need to understand whether it was interpreting our target position correctly, and that it actually was correctly disappearing off, but to somewhere we hadn't planned, or whether it was something in the way the software is interpreting that creates errors. So we need to do some investigation. We have the data extracted from the boat already, so as we'll be able to look at that and work our way through, and hopefully it'll be a relatively straightforward thing to fix, that we can get back on the water.
The lake is not long enough for us to get really high speed, so what we're doing initially is checking that the control systems all work. So this is, you can imagine that it's not like a model maker standing on the shore with his model boat. You cannot control something that this model is meant to have a speed of over 200 miles an hour itself. So the a model, a man standing with a radio control unit on the shore can't keep up with it. It's instantly, you just see a ball of spray, you won't know which direction it's going and you won't know how far it's gone. So it has to be an autonomous machine. It has to drive itself. So it needs GPS signals and GPS aiming points. And so the electronics have got to cater for that. So you've got one set of electronics doing the height control. You've got another set of electronics doing the steering part of it, and it can't turn. You've got to put limits on it because, of course, at high speed you can't whack the steering right over. It's got to be tiny amounts. It's not designed as a circuit racer. It's designed to go in a straight line. We steer it with the rear foils. Rear foils are mounted on vertical struts, and those struts steer with the foil on the bottom. And it does seem to respond to the steering at low speed, but they're not very large, those surfaces, so it's quite, you need to be able to maneuver it to a certain extent. You won't be able to do tight turns, but to a certain extent you do need to be able to maneuver it just to bring it onto course after starting. So there seems to be enough response in the steering to do that. When we get to higher speeds, the steering inputs will have to be very, very small, tiny. So it's getting degrees of things worked out is the problem. First we get it actually working, so things go in the right direction. The foils change their angle of attack correctly. Then we've got to work out the degree to which they do it, and then the rate at which they do it.
Geofence. Yep. Perfect run.
Your point is there.
Well, let's just talk about the overall situation. Basically, we set this up to try and understand the boat and get some experience with the boat. We've most certainly done that. The first Beresfield 1 was a failure. We had a lot of trouble with the software, and Leeds put a huge effort into this. About 90 man days have gone into this to try and get this software right and so on. So it certainly paid off, and we've had some spectacularly good runs. We've also had some disappointments because sometimes it just doesn't repeat what it should do, and that throws everybody into confusion. But the general progress is good. We know a lot more about it, and we're happy now to go to Scotland.
Sadly, the delays the team had experienced earlier in the year were to have huge implications, as Richard Noble explained when the team returned once more to Beresfield in November 2025.
The last time we came here, Beresfield 2, it seemed to work pretty well, I thought, really, one way or another. But then we had a real difficulty because the team there was from Leeds University, and they all got called away to go and teach, which I didn't realise was coming. So this was an awful thing. It looked as if the whole project was going to be calm for 3 months. But fortunately, the KH team have come to our help, and they've been going all day and night for the last week, and it's absolutely fantastic, the commitment. And I think we're going to get a very, very good result from this. And the thing about it, of course, is that we have to make sure that the whole boat is integral. In other words, it will meet the test requirements. And we didn't quite make it last time, but we're going to make it this time. We're into a completely different standard and also some different sort of software, which is good. So I'm hopeful we're going to get good results. But of course, as you know, like Canute, we don't control the weather. And so what's got to happen is you've got to choose a day, try and get everybody together, and hope to God that there isn't going to be too much wind, or it isn't going to be raining or snowing or whatever. We're doing a different sort of education this time. Basically what we're doing is building up relationships with these various universities. We've got quite a number of universities now. I think we're coming up to 5, which is great. And what they're doing is they're going to take an element of the project, they're going to help us with that particular element of the project, and also they're going to make it available online in simple terms so everybody can understand it. So as an example, we've got to deal with performance, we've got to deal with structures. Structures, of course, is a crucial one. Basically the hydraulics. At the end of this, everybody's going to know everything there is to be known about hydraulics. It's going to be fascinating, actually. It's a complete revolutionary way of teaching.
I'm Matthew Keir from KH Unmanned.
And I'm Peter Hall, I'm the H in KH Unmanned.
So we've come in to fit a new autopilot system and get that talking to all of the existing systems that were in the boat. And now we're looking to start proving out that system and tune the system specifically to this boat. Our business specialises in putting hydropilot, an open source, like pre-proven system. And we do this. We come to clients and put our stuff in their vehicles. So that's exactly what we're doing. We're taking a pre-existing system, we're putting that into the thrust boat to get it operating.
And there's a little bit of customization to talk to the turbine and to control the foil. So there's a little bit of customization, but the core functionality is standard hydropilot. Lots of people will be familiar with this. We've got a standard like RC transmitter that you might fly a plane or a multi-rotor with. So that's fairly standard. And then we've got mission planner here, so we're running hydropilot. We've got a mission planner, and they're just got the boat at the dock here at the moment, and then they'll bring it out. You can see we're operating within this geofence area here, and obviously it's complaining at us. We're outside the fence boundary, so it's not very happy with us at the moment.
Okay, so that's real-time GPS data coming into that.
Yeah, exactly. So it's a real-time connection with the vehicle, giving us the feedback of obviously the position and lots of other states here as well. Okay. So that's sort of very general stuff. So if you're flying a plane or a multi-rotor, you would use exactly the same stuff. And then on this second screen, we've got a bespoke panel here to this vehicle. So we've got some engine stats, and we've got some configuration for the foils, which we're not running yet, so that's why they're all reporting no voltage, because we haven't, they're not actually turned on at this stage in the trials, but soon we're hoping to get all the foils working. The key thing here is the engine telemetry. So we've added this custom interface so we can keep an eye on the engine.
A big advantage of using hydropilot is that we're sort of standing on the shoulder of giants, in that some very clever people have written our state estimator, which we also call an extended Kalman filter, or EKF. And that's fusing a whole bunch of different sensors, so the accelerometers, the gyros, we've got the GPS, we've got the magnometer for the compass, and heading. So that all that data is all being fused to help build up or kind of contribute to that model as to where this vehicle is in space. And so it allows us for doing things like error checking. It allows us to be more precise than any of the individual sensors, because they have different attributes like the speed of response versus the absolute certainty and that kind of stuff.
The intent of this first run will be to have the engine at idle and for Matt and Pete to steer the boat under the RC controller, just to show that actually does it. Then they'll do gentle turns up, heading the direction towards the top end of the lake.
I'm actually amazed, because we've got really quite a high wind here, and it's been creating quite a fetch. And there've been, certainly at this end, there's some waves of 4 or 5 inches. Down the other side, not so much, but the boat is running so beautifully. It's just hugely impressive. It's Sloan's hydrodynamics, which works so well. It's not sucking up vast quantities of water. It just fills us all with hope. We've got a real chance, we've got a real chance of making this big time. The whole teamwork thing seems to be working really, really well. And a lot of things, of course, always need constant adjustment and trimming and everything else. We're getting there. The next move is the 200 mile an hour test.
With the model and the team now ready for high-speed testing, it's time to see if our computer simulations match real-world data. We're heading for a much bigger space to allow us to run C3.2B at speeds that will test the hydrofoil concept that is key to our water speed challenge. Subscribe to our channel and we'll let you know how it goes.